12.1 is all about limits. Your definition of a limit: if f of x becomes close to a number L as x approaches c from either side, the limit of f of x as x approaches c is L. Right, essentially, if you have some graph for f of x and it's just graphed regular xy plane, whatever it is, this would be my c. So as I get closer and closer to c, I'm looking at what does my graph look like it's going to hit. And my graph could be all the way up here. If this is c, I want to know basically what does my graph look like it's going to be right there. And I say look like because it's not necessarily what is it exactly. Like it could be if there was a hole there and this point was up here. The limit's not asking what is that point, it's asking what does it look like it's going to be. So if I was coming towards it from either direction, what does it look like it's going to be? And so we read this as the limit as x approaches c of f of x, and it is L. So that would be like the y value there is L, or here would be L. To find each limit, one option would be to use a table. So that's our first option. So for that table, we want to know the limit as x approaches 2. So I'm going to make 2 the center of my table. And on either side of my 2, I'm going to be just like a little bit away from that. So right before 2 is like 1.999. Like, yeah, really that close. Right before that would be like 1.99. Right before that would be like 1.9. So hopefully you see that pattern. 1.9 is really close to 2. Closer than that and closer than that. So like all the way over here is going to be 2.1. A little bit closer would be 2.01. A little bit closer would be 2.001. And then from there, I'm going to be plugging these numbers into my function. So like if I plugged 1.9 into 3x minus 2, I get 3.7. Continue plugging each of these into your function, your 3x minus 2. Right, now notice that I didn't actually fill in where the 2 was just yet because I'm not really concerned with what is 2. I want to know what it looks like it's going to be. So as I'm coming from the left, 3.7, 3.97, 3.997, that's approaching 4. As I come from the right, 4.3, 4.03, 4.003, that's approaching 4. So it is approaching 4. That is my limit. So my limit is 4. Now, coincidentally, it is also 4 when you plug that in there. That is not always the case, and we will look at how to figure that out. For this one, I'm doing the limit as x approaches 0 of this lovely function. So the center of your table should be 0. A little bit more than 0 would be 0.001. A little bit more than that would be 0.01. A little bit more than that would be 0.1. And I normally just say the third away, like that third column away is just a tenth from wherever my thing is. So a tenth to the left of 0 would be negative 0.1. Then I'm going to get a little bit closer with this negative 0.01. Then even closer with negative 0.001. And I'm plugging those numbers in. Take a minute and do those and leave the 0 blank so we can look not necessarily what is it, but what does it look like it's going to be. Looking at my table, 1.95995, that looks like that's getting closer and closer to 2. Coming from the right side, 2.05, 005, that's also getting closer and closer to 2. So 2 is my limit. Now if you plugged this in, you actually got undefined right here. Your limit is not undefined. Your limit is the 2. Sometimes I'll say use a table. Sometimes I will say numerically. And that's using your table for that. Another way would be to do it graphically. So if you graphed this function, there's actually a little bitty hole right there, right at 0. It looks like it should hit 2. It doesn't, but it looks like it should. That's why my limit's 2. Again, it's not what is it, it's what does it look like it should be. This would be how to do it graphically. I want you to try to find the limit for this one on your own first, but do it graphically. So it looks kind of like a parabola, but there is this hole here, right, where at 1, 2 is what it looks like it's going to be. So it looks like, if I ignore what's actually happening here, if I come from the left and look at it, it looks like, oh, my y value is going to be 2. If I come from the right, it looks like my y value is going to be 2. And I'm really only focused in on that x value of 1 to see what the graph was. So since it looks like it's going to be 2 according to my graph, that is my limit. Down here, this is a piecewise function. Again, you're going to be doing these graphically. Do remember to graph these. So f of x equals 2, so that would be that straight line here at 2, for all x's that are not 3. So it's going to be 2 right there, all the way up until 3. It's not going to, when x is 3, it's not going to be 2. But I'm going to have a straight line going across there for every other x. When x is actually 3, my graph is down here at 0. So if I find the limit as x approaches 3 of f of x, what does it look like it should be? Well, it looks like it just stays on that line like the rest of the graph does, which is at 2 for that y value. So it looks like the y value would be 2. It's not. That's not the question. The question is, what is the limit, which is essentially, again, what does it look like it's going to be? Here you're finding each limit. I want you guys to try to do these 3 on your own graphically. I'll give you, pause it for a couple minutes so you can do that. I will get my graphs drawn up here and then we'll talk about them. Make sure you've already attempted these on your own first. I'm going to look at the first 2. They were pretty straightforward graphs, and yes, you could use your calculator to graph these. I'm fine with that. I'm looking for as x approaches 0, so I'm just focused in on what x is 0. If I come from the left, it looks like it's going to be down here at that -1. If I'm coming from the right, it's going to be a +1. Look right at 0. I'm coming from either side. It doesn't seem to be zeroing in on anything. Like, it depends on which way I look as to what it looks like it's going to be. So since it's coming to 2 different spots, my limit does not exist. Down here, so I look at 0, so I'm looking basically at my y-axis. From the left, my graph is getting higher and higher and higher, almost like it's going to infinity. If I come from the right and I zero in there, going higher and higher, like it's going to infinity. So they are both going to infinity. Infinity is not a place. It does not actually exist. It goes on forever and ever and ever. So if your limit looks like it's going to be infinity or negative infinity, your actual limit does not exist. When you graph this one, do make sure you're in radian mode. It will make it a little bit easier. And also, keep zooming in on the graph to see if you notice anything. Like, I zoomed in so far, and it almost looked like my graph was just going like this, back and forth. And if you maybe make a table and look at some of your values, we will actually see what those values are. So we are going to make a table for this one. So, yes, I realize that you may not be able to come up with this table on your own. That's why I'm giving this part to you. But if I'm doing sine of 1 over something, I think about like my unit circle. Like at pi over 2, my sine was pretty obvious there. So instead of doing pi over 2, that's why I use 2 pi. So my sine there is going to be 1. Instead of doing 3 pi over 2, I did 2 pi over 3 because essentially 1 over that just flips it. So my sine there was -1. Again, I would not ask you necessarily to come up with these x values of something as complex as this, but like we did on those previous couple of slides, that I would expect you to be able to come up with. And actually, if you keep plugging these in, sine of 5 pi over 2 was 1, 7 pi over 2 was -1, 9 pi over 2 was positive 1, 11 pi over 2 was negative 1. It's just oscillating back and forth between that. And the more you zoom in, the more you're going to see it jumping back and forth like that. So since it's oscillating, your limit as x approaches 0 does not exist. These are all three different situations where your limit will not exist. And I have those conditions listed out here. The limit of f of x as x approaches c does not exist if any of the following conditions is true. So x approaches a different number from the right side of c than from the left side. That's what we saw on number 1 on that previous slide. If f of x increases or decreases without bound, so that'd be going to like infinity or negative infinity. That's what we saw in number 2. And then number 3, if f of x oscillates between two fixed values as x approaches c. So because I was going back and forth between 1 and negative 1, that would be my oscillating between two fixed values. Again, limit does not exist. Now, when the limit is there are some fun properties for it. If I say find the limit of b, so maybe I say find the limit of 4 as x approaches any number you want, the limit's going to be 4. Like there's no x here, so there's no x to plug this into. If it's just the limit of x, that is whatever you're looking at, is c. If you have an exponent here, like you could take this number and plug it in. If I have x approaching c and I do the nth root of x, we'll be doing the nth root of c, and you'll see these with these next examples. A few more operations you can do with these. So let's just say, for example, I took the limit of some function f, and as this is as x approaches c, and L is my answer. Over here I did the limit of this other function because it's called g, but still as x approaches c, so I'm going to the same place. My answer was k. If I tell you the limit of some number times f of x, so it's the same as this, there's just like a number out front, then you're just going to do that number times your limit. If I told you the limit and you were supposed to add f and g inside that function, then you could really just add your answers or subtract them if it was subtraction. Your product, if it was multiplied again, you just multiply your two answers that you got over here. Same with division, of course, making sure that that limit for g was not 0 because you can't divide by 0. And same with your powers. So looking at these, the limit as x approaches 4 of x squared. We're going to use a method called direct substitution. And actually you will pretty much always try to use this method unless I tell you to use a table or a graph. And that's where you just plug it in. So 4 squared is 16, so my limit is 16. Here, there's nothing to plug my 4 in. It's the limit of 5, so my answer is just 5. Try 3 and 4. Pause it if you need to. I got 19 when I plugged in 4 on number 3, and on number 4, I got 19 over 3. If you did not get those, check them and try again. Want to go back to your does not exist ones to show you why we didn't do direct substitution back here. If you plugged 0 in here, that would have been something over 0. You can't have that. That's why we looked at the graph. Now, just because you can't have 0 in the denominator does not mean that it's going to be does not exist. But if you get 0 in the denominator, you need to check your graph and see what the limit is. I will show you in a few days a couple of methods to use when you have 0, especially if it's like 0 over 0. But for now, if you get 0 in your denominator using direct substitution like we do over here, you can't just say it doesn't exist. You have to check the graph. Pack out.